this touchy issue of touch. It's a touchy issue. What is that all about? Well, it starts with quantum mechanics. It really is a hangover from classical mechanics, right? Because it really comes from the days of Fresnel and Faraday and Maxwell. And these fellows, right, they came up with this notion of what light is. Okay, it looks more or less like this. Okay, I think everybody who's been in high school have seen this more or less, right? And you've seen this, and they say it's the wave. It's the electromagnetic wave, a transverse wave. Okay, and they explain a little bit about that. Well, they describe it. They say, yeah, it goes forward, right, one way, etc. But what are we staring at? Well, we're staring at a bunch of arrows there, and those arrows are vectors that comprise these so-called fields. Okay, so the electromagnetic wave is made of two fields, an electric and magnetic, that run at 90 degrees to each other, and each one of those is made of vectors. And what's a vector? Magnitude and direction. So this is a mathematical concept, okay, a mathematical concept that they put in motion. That's when it becomes very scary. And the other thing you should note about this, it goes one way. It goes out of the atom and out to nowhere. Okay, that's the notion that we have today of the wave, electromagnetic wave. And what we've done here is we replaced this with a more physical model. We're saying what they've confused all these years, the 200 plus years, is they mistook a rope for a wave, what they call a wave, the electromagnetic wave, a transverse wave. Ours is a 3D rope, okay? Two twined threads. Okay, that's what it's always been. And so you can see that they're similar in construction, in architecture. Okay, and you can see why the one runs 90 degrees to the other. It has no other choice. You can see something else. The two threads, when they're pulled tight, right, from the ends, they embrace an imaginary axis that runs through, the middle of the rope, you could say, the center of the rope. It's not an electric field, but an electric thread and a magnetic thread. A thread is an object, a field is a concept. So when people say, Bill, all you did was give it new names. No, then they did not understand. Field is not a physical object. They never had a physical object in mathematical physics. The only physical object that you can, to some degree, point to in mathematical physics is the particle. And even that's not a physical object because it's usually zero-dimensional, and they're really talking about numbers and units. So even the particle, the famous particle, is not a physical object. Okay, but for sure, a wave is not a physical object. Neither is a field. Neither is a vector. And what we're talking about here is not a field, but a thread. Thread like your sewing thread. That's what we're talking about. It's a thread. It's a little fiber, okay, a little hair. Any way you want to describe it, doesn't matter. I guess you get the notion. We're talking about a pair of twined threads, okay? And the good thing about this, it's torsion, right? Torsion is much faster than any wave that you can imagine. It's the fastest thing imaginable, in fact. Nothing can travel more faster than the torsion, okay? Because it doesn't go anywhere. It throws in place, and you already feel it at the ends, okay? And it's bidirectional. It goes in both directions. That's why you can see me and I can see you instantaneously, almost, here on Earth at least, right? Okay, so we're replacing the electromagnetic wave with a physical object. We're saying there's something called a rope, electromagnetic rope, okay? That's where the difference comes in. That's where we start. And here you can see them in motion, okay? Here, let's look at them. Here's the electromagnetic wave that comes out of the atom. It's this energy that comes out of the atom. And what you have really is the back and forth motion of the electron bead. We don't know why it goes back and forth between energy levels. It just jumps and, from a lower energy level to the higher one and vice versa, right? And when it does is absorbs and emits these waves, these electromagnetic waves in one direction. And what we're saying is these people have confused, what you see below for what you see above. What we have is a membrane that expands and contracts, and that gives it its maximum extent. You can say maximum orbital, minimum orbital, that in the case of the hydrogen atom, that the membrane can have. And when it does, it torques the rope. That's what we're saying. And all atoms are physically connected. That's physically connected by this rope, this electromagnetic rope, this structure. And they all pumping back and forth. The atom is simply a little heart that pumps back and forth, and by doing so at great speeds, it torques the rope. And then what you have is that the torsion travels in both directions, because essentially what light is simply a thump that the atom receives at the edge of the membrane, okay, which is the electron membrane, the electron balloon. Okay, that's what it is. Okay, and so that's the model that we're proposing. It's a physical model compared to the mathematical model proposed by mathematical physics. And here you have another version of this. Okay, again, that's the quantum mechanics model. Okay, so, well, it's the same one, sorry. Okay, so you can see the difference between what mathematical physics proposes and what rational people propose. Okay? What their model is irrational. There is no such thing as a wave. Wave is a concept. So is a field. So is a vector. All they're talking about is mathematical concepts, which they put in motion, which is very scary stuff. Okay, so what can the electromagnetic rope answer? Well, it can answer several questions. So if people say, well, why did you select this nonsense, Bill? Okay, let's go with the nonsense. That's why we propose all this. Okay, here's the first one, electromagnetic wave. You can see it's just a concept. It's nothing. It's just a mathematical concept which they bring into physics indiscriminately. And you can see the electromagnetic rope, on the other hand, meets all the requirements of what we've verified over all these years, which we've at least inferred from the behaviors of light. And that is, you have length, you have amplitude, okay? It embraces an axis, an imaginary axis, okay? And one of the questions it answers is why little c, why the velocity of light is a constant, okay? You have frequency times wavelength, okay? That's been settled, okay? If you don't understand that, well, you got to go to school and learn it, okay? If frequency goes out, wavelength had better go down and vice versa, because they are inversely proportional. And you can see why with a rope. Rope is a perfect model. That is the equation of a rope. If you torque a rope, the more you torque it, the more links you're going to get, and each link, wavelength, link length, right, it's going to be shorter. And vice versa. If you untorque the rope, well, what you see, the links getting longer, and you have fewer links for a given length of rope. Period. We're done. We have an explanation for why little c is a constant, because it's mediated by a rope and not by an electromagnetic wave, whatever that is. Okay. Okay. What else can we explain? Well, we can explain why the speed of the train is not added to the speed of light coming out of the train. In other words, the speed of the source is not added to the velocity of light. Okay. And here you can see why, because the atom goes along the rope. Okay, it slides along the rope like a bead on an abacus. The threads make up the atom itself. So it's not like it's a separate entity. It's made of the threads as well. And one thread goes around and forms the electron shell, and the other one goes straight through and forms the proton dandelion, or proton star as we call it. Okay, and so when it goes, one thread moves around and just keeps going behind it, and the other one goes through the center in the direction of motion, obviously, right? So if we have an atom moving towards another atom in a straight line, perfectly straight line, it just eats into the rope. And so it can't exceed the speed of light. That's one issue. And the other one is that you can see why it's not adding to the speed of the rope. The rope keeps torquing at the same speed. All you're doing at best is changing the frequency for the wavelength and vice versa, since they're inversely proportional. Okay, so here's another thing we can answer. This is entanglement. People don't understand entanglement. Say, oh, entanglement, it's so mysterious, right? What is entanglement? This particle affects that one instantaneously. Okay, no time involved, right? It's instantaneously, they say, right? Even though they're at opposite sides of the universe, right? And there's no mediator. And what we do, we put a mediator. We call it a rope. And there it is. Okay, and you can see why these people measure always that in one region it's clockwise and the other one is counterclockwise. Just take any rope and have your friend look at it from the other end. You both look at it from opposite ends. Well, for him, he'll see that if you torque the rope, right, the rope is torquing maybe clockwise. For you, it's going to be counterclockwise, and vice versa. Okay, very easy stuff. Entanglement is not a mystery in physics. It's only a mystery in the religion of mathematical physics. That's where they don't know what entanglement is. Okay? Very easy stuff. Really, it's baby stuff. It's kindergarten stuff. Once physics, remember, is for kindergartners. It's for babies. It's for 5-year-old children. They can understand physics. Math, you need to go to the university. I mean, if you're going to do like I did, years of calculus and so on, yeah, you have to take courses at the university level, right? Because you're not going to learn calculus overnight unless you developed it like Newton, reinvented the wheel. But you got to take courses to understand math. You do not need to take anything to understand physics. How did the window break? Well, the window broke because I threw a stone through the window, and that's how it broke. See how easy it was? A child can understand that. How did the horse move from A to B? Well, I pulled on the rope that was tied to its neck, and I pulled it over. See how easy, how difficult it was to do physics? So how does gravity work? Okay. Why does this fall downwards? Well, because every atom of this thing, right? It's a straw, by the way. Every atom is bound to every atom on Earth. Physically bound to every atom on Earth. If we could see all the ropes, we had God's eyes, and we could see all the ropes connecting every atom of this to every atom of the Earth, we'd say, oh, that's a piece of cake. That's no mystery. I can understand it. A child can understand it. But it's only when you don't see these things that people say, oh my God, how did that straw fall downwards? I don't understand it. Okay, we can also answer the slit experiment. Piece of cake, easy stuff, kindergarten stuff. Okay, here it is. Here's the slit experiment. They do it with water waves, and they say, look, the water waves interfere with the other water waves, and the problem is that water waves are not transverse waves like like light is supposed to be, but they use this simulation, which is an incorrect one, or it doesn't match what they say for light, right? Transverse wave. That's not what water waves are. They have a longitudinal component as well. And they never talk about the longitudinal component of light waves, right? Electromagnetic waves. How do we do it? Very simple. We do it with ropes, every atom around the slit, both slits, right? They're connected to every atom on the screen. They're already connected before you turn the light on. When you turn the light on, all you're doing is stimulating all these atoms. They're pumping at a higher speed, and that torsion is relayed to the atoms on the screen. And what you see is that they're offset because some are farther away than others, and because of that, the angles are not the same, and that's when you get constructive and destructive interference. But what quantum mechanics will never be able to answer is the needle experiment. Okay, the needle, really known as the hair experiment. It's Newton's hair experiment. And the reason people are not aware of the needle experiment, right, is they never read history. They never look up the original papers, the original manuscripts. If you go back and look at Thomas Young's papers, you'll find the fourth experiment that he ran was with a hair. See, he did the slit experiment, but nobody pays attention to the most important experiment, which was his fourth experiment, which was with a human hair. Okay? And so he had a hair, and he did the same experiment and also verified that there were fringes. And he did not come up with that. He said that Newton was the first guy who came up with that. That's why, I call it Newton's hair experiment. Here's a picture of Young doing his experiment not with double slits, but with a needle. In this case, he did it with a hair. I do it with a needle, which is much more comfortable to do. Okay, and it turns out you produce the fringes anyways. Okay, and here's a picture of that, how I did it sometime in the past. Okay, I put a needle on a cork. Okay, and just shone my laser against it from far away, about maybe 8 meters or whatever, and you can see at the far wall there's a little dot, a little bright dot, and that's what it looks like when you get up close to it. You can see the fringes. Okay, so there's interference already there. You can do it at home very easily. Just take a laser pointer and put a needle in a cork, shine it in there, and you'll verify what I verified, which is Newton's hair experiment, or if you prefer, the needle experiment. Okay, but again, I give credit to Newton, unless Newton stole it from someone else, I don't know, but that's what Thomas Young said. Okay. Anyways, Newton's hair experiment is a better way of doing the slit experiment. You don't need slits. You don't need to measure the width of the slits or any nonsense like that. All you need is a needle in between something very thin. You got a hair, do it with a hair, and you can point the laser at the needle or at the hair, and you can see, the fringes on the far wall. Okay, so you can do that in the safety of your house. Verify that you get the fringes, and it destroys the religion of quantum mechanics, because this religion says that you have to bounce either the particles or the waves against the edges for them to bounce back in. And here's one fellow, he's a university professor in Canada, and he illustrates that. Here it is, okay? And so if you see this, give it a second here, it's going to start. You have the slits, and they bounce them against the slit, to the sills, to the window sills, the edges of the window. But if you replace get rid of the windows, if you just leave that there, now what's it going to bounce against? Either particle or waves. You're not going to be able to reproduce the fringes, okay, because this is with bouncing, okay? And if it doesn't have anything to bounce against, then that particle is not going to come inwards. That's the problem. See, and it turns out that, you can produce it with a needle. That means that eliminates the particle and the wave all in one shot, okay? You do it with the needle experiment instead of the slit experiment. And in fact, I proposed an experiment in the past for those who have the equipment to do it, right? And I call it the slit in a vac. Slit in a vacuum, okay? You put the slit experiment in a vacuum, okay? And what you do is you put your setup there, glass enclosure hopefully, right? Or quartz, right? And you put your laser at the needle. And we're going to do this with a needle, right? And what you're going to do, you point it at the needle, and you produce the fringes on the screen. You verify that first, right? Okay, you got that? Okay, now you pump the chamber down, and you pump it down, cryo pump, or, first you do what's called a roughing or a mechanical pump, to the -3 torr, right? I used to work with pumps a lot and with vacuum equipment, and then you tie it into either a cryo or a diffusion pump, and you pump it down. We used to work in the -7 range, but if you can do better, that'd be great. So what's the point of this experiment? Well, the point of this experiment is to destroy the religion of quantum mechanics and this nonsense about particles and about waves, okay? Because quantum mechanics predicts, they do predictions in the religion of quantum. They have all these astrologers, palm readers, and so on, and they do predictions. And that predicts that once you remove all the air, water, gases, whatever's in your chamber, once you remove that to the extent that you can, right, your mean free path has increased. That means your intensity should go up, okay, because now you don't have any blockage, you don't have any things preventing light from reaching your photosensitometer or photomultiplier, whatever you use there. Under the rope model, it's the other way around. Since you're removing atoms that relay, right, the signal from atom to atom all the way to the screen, now you're removing all those atoms from your chamber. Now it's a perfect vacuum, right? You would have from the edge of the needle all the way to the screen, you would have a single rope. That's all you would have. And so either the intensity should drop or stay the same, but never increase like quantum mechanics predicts, okay? So anyways, anyone who has the equipment should try it out, okay? But yeah, I mean, there's many ways to destroy quantum mechanics, the religion of quantum mechanics, because you cannot do anything. You cannot simulate any experiment ever done with particles. You cannot. It just is irrational to do it with particles, with discrete particles. And that's why quantum mechanics had to invent the particle, which is not the corpuscle, the classical corpuscle they had to do it with, the quantum particle, which ain't a particle at all. It's not a grain of sand. You're not talking about a speck of dust. You're talking about a number. You're talking about a value, quantities. That's what they deal with. They can't put particle, the word particle, in an equation. They have to put a number, a value, a charge. What's the charge on it? Or what's the mass? That kind of thing. That's all they can do. Okay, so what's the ultimate thing that builds our universe? This is what our universe looks like. The mathematical physics one is full of particles. Whether you're dealing with space-time, an event. What is an event? A point in space-time. Or whether you're dealing with ether, or whether you're dealing with virtual particles of quantum mechanics, it's all particles. A bunch of particles that are just shaking there. And the rope model says, no, what we have in the universe is a single thread, okay? It's kind of like a double one there, but it's a single thread. And that single thread goes throughout the universe, okay? And if we started out one atom and follow just one thread of the rope all around the universe, we would end up at our starting point, because it's a single closed loop thread. And so what we propose is this. We're saying that we have a single closed loop thread. That's the entire matter in the universe. And this single thread essentially twines around itself, forms all the atoms and the ropes that interconnect them. So we're all connected, physically connected, not like they say in Buddhism or Hinduism or some other people who say, oh, we're connected. Yeah, connected by what? By energy. Well, energy is not a physical object. You can't say we're connected by energy or by thought or by consciousness or anything like that, spiritually or whatever. No, we're connected physically. There's a thread, a pair of threads twined pair of threads that connect every atom in your body to every atom in my body and to every atom on Earth. Okay, and so that's the proposal. Okay, so that's what we're proposing. Now, what's the problem with this? Well, the problem with this that people find is they say, well, Bill, all those ropes, don't they crisscross? Don't they get tangled? And no, the answer is they go through each other. They can superimpose. And that's when people say, oh, but you have an irrational assumption. I can't picture that. In fact, one fellow says the following. I had one more issue there, and that's before I continue to that, and that is that the rope model also explains the principle of equivalence. Okay, for those of you who are familiar with that, I'm not going to go into detail with it, but here it is. Okay, principle of equivalence is that if you take force equals mass times acceleration versus force equals g, Newton's gravitational equation, which is force equals gravitational constant g, mass 1, mass 2 over distance squared, which is really not a force, it's tension, right? Under the rope model. We can not only explain weight, what weight is, which is a static concept. It's the number of effective ropes connecting an atom at a given distance from the Earth, in this case, in this example, right? And it doesn't matter if the atom is moving outwards or coming towards the Earth, right? Gravitationally falling to Earth or flying outwards, it wouldn't matter. Einstein used his elevator experiment to talk about this. Well, imagine that atom being in the elevator. It doesn't matter if the elevator goes up or down, and it doesn't really matter. How many effective ropes are connecting that atom to every atom on Earth at that specific location? That's weight. That's the weight of that particle, okay, at that distance. If it goes farther, it has a different weight. If it gets near, it has a different weight. But at that distance, if we freeze the universe, if we stop the universe, all motion, all we have to do is count the number of ropes, and that's a measure of the weight of that particle at that distance. Okay? And that's why, yes, principle of equivalence is not something you measure like the mathematicians are trying to do even to this day. No, it's something that falls squarely within the rope model.